Today we will learn principal stress, a backward approach. So before moving to this new topic, let's revise what we have learned so far. So far we have learned about the Cauchy stress, principal stress, and Mohr circle. Let me remind you how Cauchy stress formula was derived. In order to derive the Cauchy stress formula, a plane was taken like this. A plane ABC was taken, which is shown by the shaded line, and it has direction cosine nx, ny, nz, and characterized by a outward normal n shown by this blue arrowed line. And three mutual perpendicular planes OBC, OAC, and OAB had stresses like this. Plane OBC had stresses as sigma x. This plane I am talking about. OBC had a stress as sigma x, tau xy, and tau xz along the outward normal, that is in this direction. Similarly, along OAC plane, the stresses are like this. Along this OAC plane, the stresses along this outward normal is tau yx, sigma y, tau yz, and similarly for the OAB plane, we can also write. So in the Cauchy stress formula, we have seen that if we are having the stresses along any three mutually perpendicular planes, we can get the stress along the arbitrary plane if we know the direction cosine of that plane. So the Cauchy stress formula was like this, as you can see here. Txn, Tyn, and Tzn are the stress components along x, y, and z axes. Txn is along x-axis, Tyn is along y-axis, and Tzn is along z-axis. And the resultant of Txy, and Tyn and Tzn can be founded by this formula. By this formula, as you can see that Tn square is equal to Txn square, Tyn square, and Tzn square. The magnitude of the resultant stress can be written like this. Whereas this resultant stress is related to shear stress and normal stress, and the relation is like this. Tn square is equal to sigma n square plus tau n square, where sigma n square is normal stress and tau n is shear stress. After deriving the Cauchy stress formula, we have faced some questions which has led to principal stress. And principal stress was like this. Principal stress, a plane on which stress vector is wholly normal, are called principal planes, and corresponding stresses are known as principal stresses. And principal stresses were found with the help of a cubic equation, and that cubic equation was like this: sigma cube minus L1 sigma square plus L2 sigma minus L3, where L1, L2, and L3 are stress invariants. And in the previous lectures, we have learned how to find out the value of L1, L2, and L3. And also a standard method to find out the roots of this cubic equation was also suggested. However, the roots of the cubic equation are sigma 1, sigma 2, and sigma 3, and these are known as principal stresses. Once the roots sigma 1, sigma 2, sigma 3 are found, accordingly the principal planes can be found with the help of some linear equations. And after that, we have learnt about the Mohr circle in 2D plane. However, still we are left with the topic Mohr circle in a 3D plane. Once I complete principal stress, a backward approach, then we will move forward to the Mohr circle in 3D plane. So a backward approach, as you can see that if principal stress is known, then how to find out the shear stress, normal stress, and resultant stress. So I assume that we know the value of principal stresses sigma 1, sigma 2 and sigma 3, and they are along the normal of the plane characterized by direction cosine nx, ny, nz. The plane which I have shown in the previous slide, the plane ABC, and that plane has direction cosine of nx, ny and nz, and along the normal the principal stress is known. However, we don't know the normal stress, shear stress as well as other stress component. So in this approach, we assume that the principal stresses sigma 1, sigma 2, sigma 3 are known, and we are about to find out the value of normal stress, shear stress and resultant stress. So with the help of Cauchy stress, we will move forward on the Cauchy stress formula. So since sigma 1, sigma 2 and sigma 3 are principal stresses along the normal, so other rectangular component tau xy, tau xz and tau zx are 0, because this sigma 1, sigma 2 and sigma 3 are principal stresses and they are along the normal. This is the reason, that's why the other rectangular components are 0. And sigma 1 can be written as sigma x, sigma 2 can be written as sigma y, and sigma 3 can be written as sigma z. By Cauchy stress formula, we can find out the value of stress components along x, y and z axes. So Txn is equal to Txn is equal to nx sigma x. We have the value of nx, we have the value of sigma x. Sigma x is equal to sigma 1, whereas tau xy is equal to 0, so this is equal to 0. Similarly, tau zx is equal to 0, so this is also equal to 0. So as a result, by putting the value of sigma x equal to sigma 1 and nx is equal to nx, we can get the value of Txn. So Txn is equal to sigma nx. In the similar fashion, we can get the value of Tyn, that is equal to sigma 2 ny, as the other rectangular components are 0, and Tzn can be represented like this. So these are the value of stress components along x, y and z axes. Once the value of Tx, Ty and Tzn are found, now we can find out the magnitude of the resultant stress, that is Tn. The resultant stress can be found by this formula. Since we know the value of Tx, Ty and Tzn, we have to simply put the value. We need to put the value to get the value of magnitude of resultant stress. So it can be written as Txn square means sigma 1 nx square, Tyn square means sigma 2 ny square and sigma 3 nz square. And final result of this resultant stress is like this. So we have calculated the resultant stress. This resultant stress we have calculated. Now our next task is to calculate the normal and shear stress. Also we know that the normal stress can be given by this formula. Normal stress can be found by using this formula. So we have the value of Txn, Tyn and Tzn as well as nx, ny and nz should be multiplied with these Tx, Ty and Tzn. So as a result, the normal stress is like this. Sigma equal to sigma 1 nx squared, because this Txn was multiplied by nx, so that it is sigma 1 nx squared. This Tyn that was equal to Tyn was equal to this Tyn is equal to sigma 2 ny, and it is multiplied by ny, so that it is sigma 2 ny square. Tzn is equal to sigma 3 nz and multiplied by nz, so that we get the value of normal stress like this. So once the normal stress is calculated, now we can easily calculate the value of shear stress. Shear stress and normal stresses are related like this. Tn square is equal to sigma n square plus tau n square. In this expression, we know the value of Tn as well as sigma n. The only thing is to calculate the value of this tau n. So tau n can be written as Tn square minus sigma n square. Let's see what are the results. So tau square is equal to Tn square minus sigma square, and these are like this. Upon simplification, these are the values. If you can simplify, then it is well and good. Otherwise, I can give the solution or detailed derivation in the next slide.
Since resultant stress is equal to sigma n square plus tau n square, and the value of sigma we have derived. So in order to get the value of this here stress tau n square, it can be written as Tn square minus this sigma n square. And by putting the value of this sigma n, let's see what we can do. As you can see that tau square can be written as we have the value of Tn square, that was sigma 1 nx square, sigma 2 ny square plus sigma 3 nz square minus this sigma whole square. So we can expand it by using the formula a plus b plus c whole square, that is a square plus b square plus c square plus 2ab plus 2bc plus 2c. So by doing so, we can get a result similar to this. This is kept untouched and this has been expanded by using the basic formula. So this is a square, b square, c square, 2ab means 2 sigma 1 sigma 2, nx square, ny square, 2 bc means 2 sigma 2 sigma 3, ny square, nz square, that is written here, and 2ca is written like this. So now we will expand the bracket. We have expanded the bracket. Now we will open the bracket and we will try to place the common terms at a similar place. So now we have opened this bracket and minus sign has been multiplied with all the terms inside the bracket. And nx square, this nx square is taken common with nx square with somewhere else, that is here. With this nx square. Let me draw it. This nx square and nx square term in this nx4 has been taken as a common and written like this. Then this ny square and this ny square from this ny4 has been written here. Similarly, this nz square and nz from here it was nz power 4. So it is taken from here and rest of the term is written as usual. Now in the next step, this nx square is been taken common in the previous step, and 1 minus nx square can be written as, since nx square plus ny square plus nz square is equal to 1, so 1 minus nx square, this 1 minus nx square can be written as 1 minus this nx square. So we will get it as ny square plus nz square, that is written here. For this 1 minus ny square, it would be equal to nz square plus nx square with using this same formula. And 1 minus nz square can be written as nx square plus ny square using this same formula. And they are written like this. Then in the next step again, we have multiplied this nx square plus ny square and arranged with these terms. So sigma 1 nx square multiplied with ny square, sigma 1 nx square multiplied with this nz square, and it has been expanded. And in the next step, we will take common with these terms so as we can form a expression in the form of sigma 1 minus sigma 2 square like that. So now this sigma 1 nx square, this sigma 1, this sigma 1 nx square, this 2 sigma 1 sigma 2 nx square ny square, and this sigma 2 ny square nx square. By taking nx square ny square common from all these terms, we can write it like this: sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2. Similarly, we can do for ny square nz square. This ny nz square, this ny nz square, and from here 1 ny nz square, we can take a common and write the rest of the term inside the bracket as sigma 2 square, sigma 3 square, and minus 2 sigma 2 sigma 3. Similarly, nz square and nx square has been also written. Now as you can see that under the bracket we have an expression like this: sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2. That is a simple formula of a minus b whole square. That's why it is written as sigma 1 minus sigma 2 square, sigma 2 minus sigma 3 square from this expression, and sigma 3 minus sigma 1 square from this expression. This is sigma 3 minus sigma 1 square. So this was all for today, and this concept also helped us while deriving an expression for Mohr's circle in 3D. So with these derivations, let's finish my lecture for today. Thank you.